Starship Flight 9 lifted off in a blaze of power. But what happened after the smoke cleared surprised everyone. Now, SpaceX is releasing new data, and it reveals a lot more than we thought. It was supposed to be SpaceX's boldest leap toward Mars, and it ended in 2 explosions, minutes and oceans apart. But for Elon Musk, that's exactly the plan. On May 27, 2025, SpaceX launched its 9th integrated Starship flight from Starbase, Texas, drawing eyes from around the globe. This wasn't just another test. It was the first time a Super Heavy booster had flown twice. Flight 9 carried a towering list of goals: payload deployment, long-duration flight, and a brutal heat shield test designed to push the spacecraft beyond its limits. And it did. After liftoff, the booster exploded over the Gulf of Mexico. 47 minutes later, the Starship upper stage lost control and disintegrated over the Indian Ocean. But SpaceX didn't call it a failure, because every second in the air gave them what they came for: data. But before we get into it, make sure to give this video a like and subscribe to our channel, because what SpaceX learned in those final minutes might be the key to landing on Mars. Let's break it down. After clearing the tower at 6:36 p.m., Starship Flight 9 powered into the skies above Boca Chica, with all 33 Raptor engines firing in unison. The launch was not only on time, but visually flawless, a pillar of fire and cloud that roared into the Texas twilight. This was a big moment for SpaceX, because for the first time ever, a Super Heavy booster was being reused. Booster 14 had previously flown on Flight 7 earlier this year. Reusing it marked a critical step toward making Starship a cost-effective, rapid turnaround system. The ascent phase lasted roughly 2.5 minutes before the vehicle hit MECO, main engine cutoff, a planned moment where the Super Heavy shuts down its engines and prepares to hand the baton to Starship's upper stage. The handoff was smooth. Stage separation occurred without issue, and as planned, Starship's second stage, Ship 35, ignited its 6 vacuum-optimized Raptor engines. The crowd at Starbase, and tens of thousands watching online, saw history in motion. Ship 35 continued to climb along a suborbital trajectory with a peak altitude goal near 230 kilometers. SpaceX had 2 major test goals on this flight. First, to open a new payload door mid-flight and eject 8 simulated Starlink satellite payloads. Second, to evaluate the durability of its thermal protection system by flying without 100 heat shield tiles. This deliberate removal of tiles was done to see how the spacecraft would handle uneven heating, crucial for developing a shield that can survive not only Earth re-entry, but also Mars. For the next several minutes, everything appeared nominal. While Ship 35 cruised above the Earth, the Super Heavy booster was already looping back toward the Gulf of Mexico. Like previous test flights, it performed a flip maneuver, reoriented itself, and began to fall tail first toward its planned splashdown zone. This descent is always one of the most critical and complex phases, controlling a 70-meter-tall booster at high speeds, steering with grid fins, and finally lighting its engines for a controlled landing burn on water. But this time, something went wrong. Just after ignition of the landing burn, telemetry cut out. Visual observers noticed a flash over the Gulf and then silence. Within seconds, confirmation came from SpaceX. The booster had experienced a rapid, unscheduled disassembly, roughly 6 minutes after launch. And honestly, that's not a surprise. They knew it could happen. SpaceX engineers later said that the onboard computer detected abnormal behavior during the final descent and likely triggered an auto-terminate sequence. All debris landed safely within the pre-cleared marine hazard zone, which is standard protocol for these early test flights. No civilians were harmed, no environmental damage was reported, and recovery boats were already nearby. The loss of the booster is not viewed as a mission failure. SpaceX has always been clear that early Starship tests are meant to push limits, and losing hardware is expected, even helpful, when trying to collect stress data and improve engine reliability. Meanwhile, Ship 35 continued its flight, reaching near space. For a moment, it seemed this would be SpaceX's most successful Starship test yet. It had climbed higher and lasted longer than any previous flight, and by the 30-minute mark, the vehicle was coasting in a stable orbit-like trajectory across the globe, heading toward the Indian Ocean. But then, things started to unravel. At around 47 minutes in, it started spinning out of control, just as it was getting ready for re-entry, a propellant leak that killed tank pressure and knocked out the ship's RCS thrusters. No steering, no orientation, just a slow spiral into chaos. Without RCS thrusters to stabilize itself, the spacecraft couldn't point its heat shield properly. This was a serious problem. Starship is built to enter the atmosphere belly first, using its heat-resistant tiles and aerodynamic flaps to glide and slow down before performing a final flip and landing burn. But with Ship 35 tumbling uncontrollably, re-entry would be more like a falling satellite, chaotic, violent, and destructive. To make matters worse, SpaceX confirmed the payload door failed to open, preventing the release of 8 simulated Starlink units. Engineers are now investigating whether the door was stuck, unpowered, or damaged. As a safety precaution, the Starship triggered an automated safing process. It vented remaining propellants to minimize explosion risk and continued tumbling toward Earth. Ship 35 eventually disintegrated during re-entry over the Indian Ocean, with all debris confirmed to have fallen within the expected zone. No damage to shipping lanes or coastal areas was reported. Though the upper stage was lost, the flight duration of 47 minutes marked a record for Starship and offered critical thermal and structural data for future re-entry designs. Because Starship is still in its experimental phase and operates under a flight test license, every failure is thoroughly documented. Within 24 hours of Flight 9's end, the Federal Aviation Administration issued a statement confirming they would oversee a formal mishap investigation. The focus will be the upper stage disintegration, as the Super Heavy R-route was within the expected risk model. The FAA has required SpaceX to submit a full anomaly report, including all telemetry, video, engine data, and software logs. No further Starship test flights will occur until the FAA clears SpaceX's corrective action plan. This isn't new. SpaceX underwent similar investigations after Flights 1, 2, and 4, all of which ended with explosions or off-nominal results. Each time, SpaceX worked closely with regulators to redesign systems, improve safety zones, and enhance the ground software that monitors in-flight health. Elon Musk stated on X that SpaceX is already applying design upgrades to Ship 36 and Booster 15, the next vehicles in the test lineup. To some, the loss of both stages during Flight 9 may appear like a setback, but SpaceX sees it differently. From their point of view, the mission delivered on several key objectives. For the first time, a Super Heavy booster was reused, a major milestone on the path toward reducing costs and enabling rapid turnaround. The upper stage also remained in flight longer than any previous Starship, providing extended real-time data right up to re-entry. Stage separation went according to plan. Thermal performance was recorded under extreme conditions after heat shield tiles were intentionally removed, and engineers now have detailed telemetry on the tank pressure anomaly that led to the upper stage's spin and eventual breakup. These are not minor footnotes. They are crucial building blocks in a system designed to evolve through trial and iteration. Beyond its technical achievements, Flight 9 plays a growing role in shaping Starship's future with NASA's Artemis program. The spacecraft is currently slated to serve as the human landing system for Artemis 3, the mission that aims to return astronauts to the Moon in 2027. It is an ambitious timeline, and pressure is increasing. While NASA continues to back SpaceX's data-driven and rapid testing approach, each launch that ends short of full success adds urgency. To meet its goals, Starship will need to demonstrate reliable performance in critical systems. Heat shielding, propellant handling, and precision landings must all function with near-flawless consistency if the vehicle is to carry humans safely to the lunar surface and back. Meanwhile, the pace at Starbase shows no signs of slowing. As of late May 2025, more than 10 booster and ship pairs were reportedly in various stages of construction or testing. Another flight could happen as early as late June or early July, pending regulatory approval following the Flight 9 mishap investigation. Elon Musk has indicated that the internal target is to reach a launch rate of one Starship mission every 3 to 4 weeks, an unprecedented cadence for a rocket of this size and complexity. One quieter but significant breakthrough during Flight 9 was the success of SpaceX's upgraded telemetry uplink system. In past flights, maintaining communication once the vehicle moved out of ground station range was a persistent challenge. This time, data flowed for nearly half an orbit, allowing engineers to observe events in near real time as the upper stage entered its fatal spin. That insight was critical in tracing the issue back to a suspected propellant leak. For future missions, especially deep space journeys, real-time diagnostics like this are not a luxury, but a necessity. Even though the hardware did not survive, the economic model still leans in SpaceX's favor. In the world of launch vehicles, reusability remains the most viable path toward sustainable exploration. Starship may not yet be landing intact like Falcon 9, but its scale and mission profile are fundamentally different. Starship is designed for deep space, not just orbital runs, and that vision demands a much more aggressive testing strategy. Failures are part of the deal. Seen through that lens, Flight 9 was not a loss. It was another critical step in a long process, built on iteration, risk, and continuous refinement. Every frame of video, every pressure reading, every second of flight feeds directly into smarter designs. What SpaceX learns now will shape the welds, the software, the heat shield configurations of the next prototypes, and bring them one step closer to their ultimate goal, making life multiplanetary. Starship Flight 9 didn't end perfectly, but it moved the program forward. Each flight like this pushes the limits, exposes what needs fixing, and brings SpaceX one step closer to reusable interplanetary travel. The data from this mission will shape every launch that follows. And the next test? It's already on the horizon. Stick around, because the future of spaceflight isn't decades away. It's launching again soon. Subscribe to stay updated on what happens next up there.